Good day everyone, today I will present my FYP title, The Effect of Heat Treatment on Nickel Catalyst Morphology for the Growth of Low Temperature Nitrogen Graphene. My presentation consists of 5 parts, which is Introduction, Methodology, Result, Conclusion, and Future Work. Air pollution is one of the most serious problems in the world. It has different emission sources, but motor vehicles and industrial processes contribute the major part. Toxic gas such as carbon monoxide, nitrogen monoxide, nitrogen dioxide, and ammonia gas release are highly dangerous to human health and harms to our environment. Analytical devices such as mass spectrometer and gas chromatograph are used to analyze and detect hazardous gas present in our environment due to its high performance in detecting low concentration of odorless gas. However, the cost of the analytical device mentioned is expensive and bulky in size, limits their application in many areas, and mostly used in laboratory only. Gas sensor, which is relatively small in size, can be applied in various fields. Among all the material, graphene has gained attention for sensing material in resistive type for developing high-performance gas sensor due to its unique characteristics such as large surface area, high mechanical strength, and high charge carrier mobility. However, a research conducted by density functional theory shows that the interaction between water molecules, ammonia, and carbon monoxide with precise graphene is belong to physical absorption, which reduces the effectiveness of gas sensor absorption during sensing. So we will introducing a defects or dopant in graphene through chemical doping to improve the sensitivity of graphene for stronger absorption of gas molecule. In this case, we will using nitrogen as it has comparable atomic size with carbon atom and consists 5 valence electrons to form strong valence bond with carbon. And chemical vapor deposition is the most commonly used method, as it can provide a continuous, high quality, and large area growth method for graphene. Deposition method has been demonstrated to simulate graphene. It functions as the catalyst which lowers the energy barrier of the reaction and control the graphene deposition. Nickel and copper is most commonly used metal substrate and is useful for mass production, commercially available and inexpensive. There are 4 steps in chemical vapor deposition such as heating, annealing, graphene deposition, and lastly cooling. And the annealing step will directly affect the graphene produced during the graphene deposition step. And annealing also functions to remove surface contamination and oxide layer. Other than that, it also modifies surface morphology of the metal substrate. There are 3 parameters have major influence on metal surface treatment during the annealing step, which is the annealing temperature, annealing time, and the flow rate of hydrogen gas. And mostly the nitrogen graphene will grow normally at high temperature above 800 degrees Celsius. However, the nitrogen content is commonly low. So in this work, we are proposing an annealing process at low temperature, at constant annealing time, and flow rate of hydrogen gas for the growth of low temperature nitrogen graphene using CVD method. Previous work shows that annealing temperature effect on the surface of nickel metal. As we can see, small closely packed nickel island with average diameter of 80 nanometer form at 300 degrees Celsius, and the average of the diameter of nickel island increase with increasing temperature, and the resultant islands are more isolated to each other. This indicates that the annealing function as etching effect for the surface of metal in the presence of hydrogen gas, and the size and the distribution of the nickel island depend critically on the annealing temperature. Etching effect will only occur when the metal substrate annealing with the presence of the hydrogen gas, and the hash radical will play a role in etching process. And low hydrogen annealing can smother the catalyst surface as shown in the figure. And there are research shows that annealing metal substrate at low annealing temperature promotes the formation of single layer graphene and relative high level of defect, while high annealing temperature promotes formation of multi-layer graphene with low level of defects. My problem statement is high annealing temperature at constant flow rate of hydrogen gas and constant annealing time. The aggressive etching effect occurs on metal substrate causes the size of nickel island and roundness of the surface increases. Multi-layer graphene form while substitution of nitrogen atom is low. So we are introducing low annealing temperature on metal substrate to reduce the aggressive etching effect on metal substrate and improve the substitution of nitrogen in the graphene lattice. The Objective of my project is to investigate the effect of annealing at low temperature regime on nickel catalyst for nitrogen dot graphene growth by chemical vapor deposition method. The scope of my project is to investigate the effect of annealing temperature at 400 and 700 degrees Celsius with 30-minute annealing time on nickel metal substrate for the synthesis of nitrogen dot graphene. Next, we will analyze the morphology and structural on nickel metal substrate before annealing, after annealing, and after growth using optical microscopy and Raman spectroscopy. This shows the research flowchart of the system. Firstly, we will be preparing a 150 nanometer thick nickel film on SiSiO2 substrate using RF magnetron sputtering system, and the as deposit nickel film will be cut into a size of 1 × 1 cm using a diamond cutter. Deposit nickel film will undergo a standard organic cleaning to remove any contamination and oxide layer on the surface, and then it will transfer to the PECVD system for annealing process at 400 and 700 degrees Celsius separately for 30 minutes under continuous supply of hydrogen gas at 50 sccm. Figure 7 shows the PECVD system for synthesis nitrogen dot graphene. During the growth process, mixture ratio of 1:1 to 8 of benzene, ammonia, and argon act as a precursor will be supplied under the same pressure of 1000 Pascal for 1 hour. The optimization of nitrogen dot graphene will be done by applying radio frequency plasma power of 5 W with constant temperature at 500 degrees Celsius, and concentration of ammonia will be set to 20 sccm. This time chart shows the flow of the progress for the growth of nitrogen dot graphene. Data analysis will be done focused on the surface morphology and structural of the graphene on metal substrate. The optical microscopy is used to identify the surface morphology of the graphene on nickel substrate, while the Raman spectrometer is used to identify the number of graphene layer and the level of defect on nickel's metal substrate surface. This shows the result obtained for optical microscopy. As we can see, no obvious change on the surface for S deposit nickel and nickel anneal at 400 degrees Celsius. Nickel anneal at 400 degrees Celsius shows smooth and flat surface, while nickel anneal at 700 degrees Celsius have high density of black dots throughout the whole area of the sample. This means the low annealing temperature enhances more closely packed island, while the high annealing temperature at 700 degrees Celsius enhancing larger diameter island, and the resultant islands are more isolated from each other. This shows the optical image obtained after the growth process. As we can see, the density of the black dot on N-dot graphene on nickel film anneal at 700 degrees Celsius are much denser and concentrated. Denser black dot happen due to the high etching rate on nickel film, indicate that etching rate increase with the increase of temperature. Red square area and dot graphene on the nickel film anneal at 400 degrees Celsius show clear background without any black dot. This shows the Raman spectrum obtained for N-dot graphene on nickel sample anneal at 700 degrees Celsius. Higher intensity of D-band for N-dot graphene sample anneal at 700 degrees Celsius, and the number of layers is determined by calculate the peak ratio of intensity of 2D band to intensity of G band, and the ratio of intensity 2D band to intensity of G band of black dot is 0.6, and the background is 2.16, which represent the single layer and field layer of graphene formation respectively. Step to be carried out next is to further characterization of N-dot graphene nanosheet on sample anneal at 400 degrees Celsius, and to confirm the existence of graphene layer and nitrogen substitution. Next, further characterization of XPS on both samples need to be done to evaluate the doping concentration on graphene lattice. As optical microscopy not able to obtain and observe the actual size of the black dot in terms of diameter and thickness, so we will propose using a scanning electron microscopy and atomic force microscopy to visualize the surface morphology of the thin film and obtain the actual value for the size of black dot produced. Conclusion. Sample anneal at 400 degrees Celsius have flat and smooth surface compared to sample anneal at 700 degrees Celsius. The size of the black dot increased as the temperature increased. 700 degrees Celsius anneal metal substrate is dominated with few layers of graphene, while 400 degrees Celsius anneal metal substrate is expected dominated by single or bilayer of graphene. Lastly, the nitrogen atom is successfully substituted in graphene lattice based on the D-band in Raman spectrum for the sample anneal at 700 degrees Celsius. For the future work, we will prolonging the annealing time and vary the concentration of hydrogen gas during annealing to see the effect to the surface morphology of nickel metal substrate. That's all for me. Thank you for your attention.